Hey everybody, it's time for another mini lesson, and today's mini lesson is on an introduction to intramolecular bonding. Intra meaning within molecules bonding. So you've just conducted a lab on intermolecular bonding, that is attractions between whole molecules. We are now focusing on bonding within a given molecule or compound. There will be a series of videos for this. We're just going to start with some basics today. So first of all, the overview here is there are 3 categories of bonds that we will talk about: covalent, ionic, and metallic. Today, we are only going to begin to talk about covalent bonding as an introduction. The goal of bonding is always for atoms to attain greater stability. And in order to attain greater stability, electrons either need to be shared or transferred or move in some way around atoms involved in a bond. Whenever bonds are formed, there is energy released. That is creating a more stable compound. Okay? It's handy for you to have your reference tables available. I will be using information from the periodic table and from table S for this mini lesson. Okay, so as I mentioned before, our focus is covalent bonding. Covalent bonding, by definition, involves the valence electrons, if you recall, the outermost electrons of only non-metal elements. Electrons in covalent bonds are either shared evenly or they're shared unevenly. But the key word is that electrons are shared. Now, when electrons are shared evenly, we're going to call those covalent bonds nonpolar. When electrons are shared unevenly, we're going to call those covalent bonds polar. Okay, so a couple of things we need to be aware of, and there's general rules here. Okay, polar covalent bonds, again, have electrons that are not shared evenly. So there is a difference in the electron negativity of the 2 atoms involved in the bond. And that electron negativity difference is going to be between 0.6 and 1.6. You will see some examples of that coming up a little later. Now, nonpolar covalent bonds have even sharing of electrons, and the electron negativity difference, therefore, is usually 0, but it could be up to 0.5. So I'm going to do the first example, and that first example is diatomic hydrogen or hydrogen gas. And as you can see here, it's written as a molecular formula right now. Now, in order to demonstrate this nonpolar covalent bonding, we need to draw Lewis or electron dot structures for the hydrogen atoms involved here. Now, when you look up on the periodic table, you would see that hydrogen only has 1 valence electron. So the Lewis dot structure or electron dot structure for a hydrogen atom looks like this. Now, we have 2 hydrogen atoms involved in this bonding. So I'm going to draw the other hydrogen atom, and I could draw the electron as a dot, but I'm going to choose to draw it as a little X because I like to sometimes show that in this covalent bond, one hydrogen, this hydrogen, is going to contribute that little electron, and that hydrogen is going to contribute that electron. Again, these are Lewis dot structures for those hydrogen atoms. Now, what we want to do is create a Lewis dot structure for the bond. So I'm going to show it this way. Just a little neater there. So you'll notice, by the way, in this bond, this covalent bond, it involves the sharing of 2 electrons between 2 atoms. I could show this also as a dash. So while this is the electron dot structure for this compound, this would be the structural formula for diatomic hydrogen. And that dash represents 2 electrons. Now, when we go to our table S in our reference tables, we would look up the electron negativity of hydrogen, and we would find that it is 2.2. Because both of these atoms are identical, they have equal attraction for these electrons. So the difference between the electron negativity of these 2 atoms equals 0. And guess what? That means this is going to be a nonpolar covalent bond. Let's look at another example. This is another example of a nonpolar covalent bond. And we're going to use this compound here, which actually can be represented right here. It's kind of cute, isn't it? This is a ball and stick model. More of information about these coming up soon. But this here is actually called methane. And one day, really soon, you're going to learn how to name them. Compounds like this. But you'll notice that there's 1 carbon, there's 4 hydrogens involved here. This is the molecular formula for methane. So what I'm going to do first is I'm going to draw my electron dot structure for carbon. When I look up carbon on the periodic table, when I look at carbon, I'm going to see that its electron configuration is 2-4. That means it has 4 valence electrons. So I can draw carbon like this. This would be the Lewis dot structure for carbon. Now you'll notice there's only 1 carbon to 4 hydrogens. Whenever you see that kind of combination, it's going to make sense that the singleton, in this case carbon, is going to be in the center and it's going to be surrounded by hydrogens. And by the way, when you look at carbon, it's got those 4 valence electrons. It's got the making for 4 perfect bonds. Now, as you recall from the last example, each hydrogen has 1 valence electron. I'm going to draw it like this. So what I've created right now is the electron dot structure for a molecule of methane. These dots or X's represent intramolecular bonds between 2 atoms. So the carbon and hydrogen are bonded here. If we look up the electron negativity of these atoms, carbon has a 2.6 electron negativity. Hydrogen has a 2.2 electron negativity. So our 2.6 minus 2.2 gives us a 0.4 electron negativity difference. And according to the rule I just gave you, that is less than 0.5. And therefore, this is an example of 4 nonpolar covalent bonds. Now, what would the structural formula for this look like? You just put your dashes there. Structural formulas are nice because they kind of neaten up, you know, the electron dot structure. You know, it gets a little messy looking there with all those dots and X's. So this would be that structural formula. And that is for methane, which, by the way, there's the ball and stick model for methane. So you have carbon, and these plastic sticks represent the 2 electrons being shared between the carbon and hydrogen atoms. These electrons are being shared evenly because there's only a 0.4 difference. So it's considered even sharing. And when you have an even sharing of electrons, you have a non-polar covalent bond. Oh, heck, let's go for a third example. Let's have a little fun with this. Okay, so now we have 2 carbons and 6 hydrogens. Now, one thing about carbon compounds, by the way, this is an organic compound. Organic compounds are made up of carbon and hydrogen elements at minimum. And carbon is a really good chain forming or ring forming element when it forms compounds. So and that we can thank those 4 electrons, giving it a lot of versatility in its bonding. So now what I'm going to do is I'm going to draw 1 carbon. I know it has 4 valence electrons. I'm going to make the second carbon right next to it, like a little chain. Let me do that one in black. Okay, so you notice what I've done here is I've created a covalent bond between the 2 carbons. All right, we have to add our hydrogens. Now I have 6 hydrogens, and we know that each hydrogen has 1 valence electron. There's 1, 2, 3, 4, 5, and 6. So this is actually called ethane. And ethane here is demonstrating nonpolar covalent bonds. Why? Because if you recall, when we were looking at methane, the difference between the carbon and hydrogen is only a 0.4 difference. So we know that these are nonpolar bonds. Well, we've got the same thing here, but we also have 2 carbons next to each other, and they have the exact same electron negativity. So that's clearly going to be nonpolar bonding too. Let's make our structural formula. Make it nice and neat looking. And there you go. And here's my ball and stick model. It's kind of cute. You'll find that ball and stick models have a benefit of giving you a better 3-dimensional view of how those how the atoms are kind of positioned relative to each other. Okay, so we'll learn more about these in the future as well. So that's where I'm going to stop for right now. I'm going to pick up in a moment and start talking about some examples of polar covalent bonds.